Good morning, everybody. Friends, we are here again to talk about fluorescence spectroscopy. So, we gave a brief introduction of means what is called spectroscopy and other aspects. So, today we are here to discuss about this what is called spectroscopy. So, let us start. Now, before that let me remind you that these are the 3 textbooks that I generally follow, and you may follow all these 3 books, or maybe some other suitable books you can also follow. One is Principles of Fluorescence Spectroscopy by J.R. Lakovich. Then another is Molecular Fluorescence, Principles and Applications by Bernard Valure. The third one is Principles and Applications of Fluorescence Spectroscopy by Albani. So, spectroscopy means we deal with light, that is spectra. Okay, now all of you know that white light is a combination of 7 colors, and all of you learnt in your school days that this Newton's disk, okay, when you rotate it, then all the colors are not visible, and what happens is that you see only white color means it becomes white. So, white light is a combination of 7 colors, and spectroscopy, in spectroscopy basically it is the analysis of light, that is various frequencies associated with light. That light may be that will be in optical, or maybe infrared, or maybe in some other region of the spectrum. So, basically we analyze the light from something. And what is a spectrometer? So, spectrometer means the instrument which measures spectra. Okay. So, that is why it is called meter, spectrometer, something that measures. So, here it measures spectra, that is why it is called a spectrometer. Okay. And spectra is basically an ordered arrangement of something. It is not only the arrangement of different wavelengths or different frequencies in one axis, and in the other axis maybe their intensity. It may be something like, it may be age spectrum, like suppose we have a class having students of different age group, then we can arrange them, we can plot like this, like suppose say students are of age, say for example 20 to 40 years. So, we can arrange them like here number and here age. So, maybe suppose say 20 means students with 20 age, they may be say like 5 in number, say for example. Okay, say age is 20, okay, and this is number say 5. Okay, then maybe another say 40 or say 25. Okay. So, say that number is say for example say 10. In this, so if we arrange in one side say age, in other side say number. Okay. So, in that case, or maybe we can do it in a reverse fashion, like this axis age and this axis number. So, we can find the age spectrum, or we can find the number versus age spectrum. Okay, so, it is basically an ordered arrangement of something. So, in spectroscopy what we do, basically we do this in x axis we write say frequency, or say maybe or it may be say wavelength, and in this axis maybe intensity, okay, intensity, or maybe some other quantity we can do, maybe transmittance. So that I am coming to that, I mean later on. Okay, so if we plot, if we connect them with a line, we get a spectrum. Okay, spectrum, it is basically the frequency or maybe wavelength spectrum. Now this spectra can be continuous or maybe it can be discrete. Okay, spectra may be continuous or maybe discrete. Now continuous spectra means, in this case, energy at all, means we get energy at all frequencies or wavelengths, as for example spectra of sun or maybe spectra of stars. Okay, so this is one type of spectra. Now there is another kind, that is called the discrete spectra. In that case, energy at some particular frequency or wavelength. Okay, so spectra of atomic or molecular systems, where we get maybe certain frequencies are available, certain frequencies are not available. Okay, so these are called discrete spectra. Okay, now this discrete spectra, okay, this may be due to absorption of energy or maybe due to emission of energy. Okay, so basically, since we here what we do, means in spectroscopy what we do, we measure light, that is intensity of light which is coming out of some system or some source, or maybe say from some body. So basically what we do, we measure that light, okay, and we try to analyze. So that means we need to have some devices, okay, that will be able to analyze that is analyze the intensity, and also that will be able to tell which frequency is there, which frequencies are there in that particular light. Okay, now means basically spectra, whatever we are going to talk about is basically absorption spectra or maybe emission spectra. So therefore process associated with spectra may be absorption process, that is absorption of energy, or maybe emission of energy. Spectrum and spectroscopy. Spectrum is basically different colors observed when white light is dispersed through some dispersion medium. So dispersion medium could be like prism. Okay, so white light falls on that prism and then it is getting dispersed this way. Okay, so basically white light, and here various colors. Okay, so this is a dispersion medium. Dispersion medium. Here dispersion medium is prism. In some cases dispersion medium can be like which is called diffraction grating. Diffraction grating. A good example of something similar to diffraction grating is this compact disc which is not written, okay, blank compact disc. So if you see this glazed side, then you will be finding that it gives out different colors. So it can be similar to a diffraction grating. I mean basically it is not a true diffraction grating, but it looks like, it looks like to be a diffraction grating. Okay, so prism, diffraction grating, these are the good dispersion medium. Okay, and next is the alteration of light intensity as a function of frequency and wavelength. So that is important. So after, suppose after this is after it is dispersed, then maybe when that light passes through some medium, then alteration of intensity of certain frequencies may be there, and that is called basically absorption. So, alteration means some frequencies are diminished and some frequencies remain as it is. So, therefore, some of the frequencies are absorbed and some of them are not at all absorbed. So, therefore, as a result of which what happens that there is an alteration of intensity of certain frequencies or certain wave numbers. Okay. Now, then what do we do in spectroscopy? So, it is this study of spectra, okay. That is, we study spectra, then we analyze the spectra. Okay. Suppose we have got certain substance, then light is passed through it, and after it is passed, then we analyze the light which is obtained after the sample, and also we compare this light after sample with the initial light, and then we analyze what are the frequencies, I mean what are those frequencies that have undergone the alteration in intensity. Okay. So, that we analyze in spectroscopy, and also these analyses will help us in characterize certain substances. So, characterization of different substances. That means suppose we have got two different substances having different characteristics. So, then it may be possible to differentiate, or it may be possible to identify, I mean which one is which one, I mean whether the one substance is same to that of the second substance, or there are certain difference in their spectral characteristics. So, if we analyze, then that will help us in characterizing these substances. Also, spectroscopy helps us to identify interaction of various chemical systems. What are those things? Like interaction means maybe it may be binding, it may be certain chemical reaction. Suppose we have, say, think about certain chemical reaction, say for example decolorization of potassium permanganate. So, it has got some color, it is a colored substance, its color is violet. So, or maybe you can say purple. So, purple to colorless, purple to colorless. So, the thing is that when this happens purple to colorless, then surely there is a difference in their spectral characteristics of this solution. Initially the solution is purple, means its spectral characteristic is different than that of colorless substance. So, therefore, we can differentiate whether, we can say whether some reaction has taken place with the substance with which we started the journey. Okay. Maybe there may be other things like interaction. Interaction means suppose interaction between two substances, two chemical substances. There may be interaction like some chemical linkage formation, maybe some weak interaction. So, if there is some weak interaction, then what happens is that maybe there is some alteration in their spectral feature, or maybe something happens that say color is changed completely, although that is not a chemical reaction. Okay. Maybe some binding interaction, say between some protein with some drug. Okay. So, when there is some binding interaction, then what happens that the drug molecule which binds to the protein, initially it is in some solution, then after the protein is added, then since it binds to the protein, then therefore environment is different. So, therefore, we expect to have some change in the spectral feature of the drug as well as the protein itself. So, therefore, spectroscopy helps us in many ways, especially with the chemist make use of the these this spectroscopy for various processes that are occurring in chemical systems, chemical or maybe biochemical systems. So, spectra relate to various motions of the molecule. So, if you study quantum mechanics, then you will be finding that molecules or atoms are associated with a number of quantized states, and each quantized states are associated with certain motions within the molecule. Suppose we have got an isolated electron. So, its energy its energy is continuous. So, it is a free particle. So, its energy is continuous. It is basically continuously variable, energy increasing. Now, the moment you put this in a boundary, that is a particle in a box, then this continuous energy levels are converted to discrete energy levels, like this, certain number of discrete energy levels. I am not writing here in appropriate scale, but just to show you that these continuous levels are now segregated into different levels. Okay. So, therefore, these continuous energy levels are now converted to quantized energy levels. So, that means here energy is fixed, here energy is also fixed. So, in order to achieve this energy, you have to provide certain discrete quanta of energy, so that the system can be transferred from this lower level to the next higher level, and another energy to put it to the next higher level. Okay. So, these energy, discrete energy levels are very important when we talk about spectroscopy. Now, these motions are basically these motions, one is rotation, the other one is vibration, and the third one is electron motion or electronic motion, electronic motions. Okay. So, rotation, vibration and electronic motions. So, rotation means it is basically a rotation of say diatomic system, say for example it is rotating. So, this rotational motion is also quantized. It is associated with a number of discrete energy levels. Okay. So, you cannot just directly go to this unless we supply certain discrete amount of energy. You cannot go from here to here. In order to go from here to here, we have to supply certain amount of energy in discrete quanta. Okay. So, this motion is a quantized motion. So, quantized motion means suppose the molecule is rotating with a definite rotational energy. Now, if you want to change its rotational state means when it is rotating with some definite rotational energy, then it must be associated with some level. So, when we try to, or when we intend to transfer or transit this or put this molecule, that is this rotating molecule, to the next higher level, then we need to supply certain amount of energy. Okay. So, therefore, this rotation is a quantized motion. Vibration is basically say this motion. So, suppose we have got a molecule like this. So, it is doing like this. It is a vibration. It is vibration, or maybe this motion, bending. Okay, this motion. This is also quantized. So, therefore, in order to change its energy state, we need to supply certain quantum of radiation, and when that particular energy matches with the energy gap between the initial and the final state, then there is transition. So, transition, that means in other words we can say that transition means, that is, the moment you supply the definitive quantum of radiation, then then transition takes place. Or in other words, suppose your molecular system gets a definite quanta of radiation from a source of radiation, then it is expected to absorb that radiation and it will undergo a transition from the lower state to the upper state. So, therefore, that quantum is now missing since it is absorbed by the molecule. So, now if the emergent light, after it passes through your sample, if you analyze, then what you get? Simply that particular frequency will be missing, either it will be missing or it will be less. I mean, less means its intensity or its population, whatever you say, it will be less, or that means its amount will be less. So, therefore, if we can quantify that, then we will be finding that those particular frequencies or particular energies are missing in the emergent light. So, that means we can say that those frequencies are those which are missing or lowered in intensity are characteristic for the molecular system under investigation. Okay. So, if we now know what are those frequencies, then we can find out the gap between the between these two levels, that is the transition. Okay. We can find out the gap. Okay. In the same way, electron motions, these are also high energy. So, this way energy is increasing. I mean, rotation is the least requiring energy, vibration is the intermediate, and electronic motion that requires more energy. Electron motion means we have to have, say, electronic levels like this, and these electronic levels are widely separated compared to two adjacent rotational levels or two adjacent vibrational levels. Therefore, this requires more energy. So, electronic excitation or electronic transition requires more energy, and therefore, it's it falls in the higher energy side of the spectrum. Okay. So, what is spectroscopy? Basically, spectroscopy is a general term referred to the interactions of various types of electromagnetic radiation with matter. So, what does that mean? Just we have said that for rotation or maybe for vibration, in order to have transition, we need to have certain frequencies from the source of radiation, and that will be absorbed by your molecular system, okay, and then used up for the excitation to the next higher level. So, it is basically an interaction of matter. Matter means your molecular system here. Of course, for chemists it is molecular system. So, it is the interaction of matter with radiation, and this radiation can be of different types, like it can be gamma rays, it can be X-rays. This is gamma rays, X-rays, UV, then this is visible, then IR, then microwave, then radio frequencies. Depending on what are the interactions you are considering. Okay. So, generally UV spectra, UV region, this is moderately high. So, these are used up for this electronic excitation or electronic transition. Visible is also used up for electronic transition, visible and UV. IR is for this vibration. So, this is IR, this is UV vis spectra. Rotation is for microwave. Okay. Then radio frequency is for your resonance spectroscopy. Okay. X-ray, that is still higher energy, core electron excitation that is required. Okay. So, and this is the electromagnetic spectrum. So, it is nothing, spectroscopy is nothing but interaction, study of interaction of matter with radiation, and this radiation is of various kinds. Especially in optical spectroscopy, the radiation falls in the optical region, that is UV visible region. Okay. So, in optical spectroscopy, we concentrate from here to here, that is, it is UV visible, UV to visible. Okay. Now, these are the corresponding meter, centimeter, nanometer scales. These are the frequencies and typical energy in kilocalorie. Okay, you see that this side energy is very less, this side energy is very high. Okay. So, so we deal with, in spectroscopy we deal with interaction of matter with radiation. So, therefore, when if we say what is happening for in vibrational spectroscopy, so IR radiation falls onto the molecule when the IR frequency matches with the characteristic IR vibrational frequency of the molecule, then that energy is absorbed. Energy is absorbed means it gets excited from a lower level to the higher level. So, its vibrational state is changed. Okay. So, therefore, there is a transition that takes place. So it is the interaction of a vibrating molecule with IR radiation, and as a result of which some of the frequencies are missing because of absorption, and some of them are remaining. So, therefore, when we analyze the emergent light or the transmitted light, we should be able to find out what are those frequencies that are that have interacted with the molecular system, and from that we should be able to find out important information about the processes or about the spectroscopic transition that is taking place as a result of interaction of matter with radiation. So, electromagnetic radiation is particle in nature. Molecules have certain number of states corresponding to definite amounts of energy. So, as I told you that if you study quantum mechanics, you should be able to find out that this molecular systems, like an atomic system. So, there is a nucleus, say for simplest case, say hydrogen, there is a nucleus and outside there is one electron. So, this electron is having different energy levels. Depending on the amount of energy that you are supplying to it, it may be excited, or in certain cases it may be de-excited, giving rise to some radiation. Okay. So, in the same way in molecular system, when say molecule means at least we require two atomic systems for making a molecule. Okay. Like say H2, the simplest molecule you can think of. Molecule means it is a diatomic system. I am talking about the diatomic simplest diatomic system, that is your hydrogen H2. So, that requires, that has 2 electrons. So, 2 electrons will form one bonding orbital, another anti-bonding orbital. So, it is basically this bonding anti-bonding concepts all are coming out of the solution of the Schrodinger equation. Schrodinger, that is a quantum mechanical description. When you consider the quantum mechanical description of the system, you should be able to solve this equation, and then after solution you will be getting a number of solutions. Okay. So, each solution corresponds to different energy levels. Okay. So, that is why molecules have certain number of states corresponding to definite amount of energy, and these are called discrete states. So, there is no state in between. Discrete states means like this is one state, there is another state. So, there is nothing in between. So, that is the strange behavior of quantum mechanics, like unlike this one, that you will be getting all intermediate levels, but here you do not get. So, these are all discrete levels, and so discrete levels are of prime importance in spectroscopy. Now, molecules can absorb energy and migrate to a higher energy level, because after absorption, that is when this Bohr's resonance condition is matched. Bohr's resonance condition means, so if there is an initial state and there is a final state, so initial state energy and final state energy. So, when you find out that the difference between these two, then whatever difference remains, if that matches with the radiation energy, the radiation what you are supplying, if that matches, then there is a resonance condition that the system will be excited from the lower to the upper state. So, when this resonance condition is is maintained, or when it matches with the when Bohr resonance condition is followed, then the molecules will absorb energy, or the system or the molecular system or the quantum mechanical system will absorb energy and migrate to the higher energies level, which is called the excited state, and this process is called the transition. So, when you supply h nu, this h nu, say this is E1, say this is E2. So, h nu is equal to E2 minus E1, then and only then this transition will take place. Okay. Now, the energy absorbed in transition process is exactly equal to the energy difference between the states involved, what I just wrote over here. Okay. So, this is the condition, unless means if it is not satisfied, then this transition will not take place, So, this has to be followed, strictly, this has to be followed strictly. Otherwise, this quantum mechanical transition will not take place, therefore, no spectroscopic signature is expected if this is not followed. So, this is related to the spectroscopic signature, that is the spectra of a molecule. Now, energy level diagram for a typical photon absorbing system. Okay. Now, think of energy level diagrams like so when we do spectroscopy, we always keep something in mind, that we have a molecular system, molecular or maybe atomic system. Okay. So, associated with a number of energy levels, which is obtained out of the solution of the corresponding Schrödinger equation. Okay. Now, when we get the solution, then we arrange these levels in order of increasing energy. So, like this is the lowest energy solution. So, this is called the ground state. So, energy is designated like E0. Then next is the, say this is E1, first excited level. Say this is E2, second excited level. Okay. So, this is ground state E0, first excited state. So, first excited state, this is second excited state, second excited state. Okay. So, what happens that you may supply energy, as I told you, if you can supply energy which is exactly equal to the gap between these two levels, then there will be absorption. So, you supply energy h nu, say h nu 1, then the system will be transferred from this ground state to the first excited state, that is this transition will take place. Now, what will be the fate? What will be the fate of this excited state? So, fate is that generally it is found that if nothing else is happening, if it is a very simple, there is no other complication is there, then this excited state, since it is a higher energy one, it will try to lower its energy by various means, but one means can be like it will give rise to radiation. It will give rise to radiation. Okay. So, you are inputting photon and also you are getting photon out of the system. So, it will be h nu 1. Okay. In the same way, if you supply more energy, what will happen? More energy means energy which corresponds to a level somewhere over here. Then what do you expect? As per quantum mechanics and as per the principles of spectroscopy, we will say that since there is no level, this transition will not take place. Since this transition does not correspond to a stationary state of the molecule, these levels are called the stationary state of the molecule. Therefore, so this simple transition process will not take place. Okay? So, then what next? We keep on increasing the energy, then again we will get another situation that when the energy, increasing energy that matches with this gap, like here h nu 2, then again the system will be directly transferred from here to here, not through this, okay, from here to here directly. Okay. So, then it may undergo de-excitation, giving rise to luminescence, which is called the luminescence. So, I am not telling any other term, it is a general term, luminescence. So, h nu 2 will be obtained back. We will get back this extra energy. So, that means in the excited state molecules will absorb energy and go to the excited state, and then in the excited state it may undergo several other things that I am not going to talk about right now. Maybe in some other lecture we will take up the fate of an excited state. What is happening when a molecule is excited from a lower energy level to a higher energy level? What are the possible things that may happen, whether it is a chemical reaction or it is a just a physical process. Okay, so this particular aspect we will take up in some other lecture. So energy, if we think of an energy level diagram, it is a typical photon absorbing system. So, this is absorption, this is emission. Of course, this emission wavelength is lambda 1, and if this is an absorption, then corresponding emission wavelength is this. So, absorption is always indicated by a vertical line, emission is always indicated by a vertical line, and these vertical lines are drawn, there is a famous because of certain principle which is called the Franck-Condon principle. So, always this absorption process or this emission process is always depicted by vertical lines, especially this absorption process. So, this is why this is drawn through a vertical line, especially when this is an electronic transition. This is as per with the principle that is after two scientists, one is Franck-Condon. Franck-Condon principle. So, we will talk about that maybe in some other lecture. Right now, we are not going to talk on this particular principle in detail. Okay. So, typical molecular system, it is a little bit complicated. This is a typical simple photon absorbing system. Okay. This is a little bit complicated. Okay, little bit complicated. Why? Because when you talk about spectroscopy, and especially absorption spectroscopy, or if it is UV visible spectroscopy, then we always deal with electronic levels. But again, if you consult quantum mechanics, you will be finding that these electronic levels are associated with a number of vibrational levels. That means one electronic level is associated with a number of vibrational level. Then each vibrational level is associated with a number of rotational levels. Okay, that means when you talk about an electronic state, that means it must be associated with a number of vibrational levels. At the same time, those vibrational levels will be associated with a number of rotational levels. Okay. So, introduction of these additional levels in connection with this electronic state further complicates the simplistic picture that we talked about here. This simplistic picture does not remain as simple because complications come into action. Okay, so what happens then? The thing is that the moment we introduce this vibrational levels, then what happens is you look at this diagram, that this is your ground electronic level, this is an absorption process, or it is also called the excitation. Excitation means system is excited from the ground electronic state to the first or maybe second electronic level. So this is depicted by these two dotted lines. Then what happens? From this excited levels, okay, de-excitation may take place directly from this electronic level to this V0 level, okay, V0 level, that is the lowest vibrational level, or maybe here or maybe here. So what will happen, that when this de-excitation takes place, that means de-excitation means you expect to get, if it is giving rise to radiation, if it is an emission transition, then you expect not only a single frequency, it is not a single frequency, but other associated frequencies. Okay. Here you expect only one frequency, but here you see that although all these de-excitations are originated from E2, but you see its end point is like this, here it is at V4, here it is at V2, here it is at V0. So therefore, the emitted light will be found to be contaminated with more than one frequencies. Therefore, if we analyze this emitted light, then we do not expect a single frequency, but a bunch of frequencies. That is, in that case we expect an emission spectra. Okay, emission spectra, that means associated with emission spectrum associated with a number of frequency. Okay, just not one frequency. If had there been only one level like this simplistic diagram, we could get only one frequency, but here a number of frequencies. So emitted spectra is expected to have a bunch of frequencies. Therefore, we get a spectra. It is not a single line, we get a spectra. So if we plot that, it may look like something like this, not like a single line spectra. It won't be a line spectra, but it will be something like a band spectra. So here your frequency nu bar, and here is your intensity. Okay. So gradually, we the situation is getting complications because of introduction of these new levels. So your spectra becomes also complicated. So what is now then since we deal with electronic spectroscopy, or UV, deal with UV visibles absorption, or since we deal with electronic level, so correspondingly UV visible absorbance spectroscopy is the place where this particular type of electromagnetic radiation, matter radiation interaction is discussed. So in visible, it is basically 380 to 780 nanometers. In some books you will be finding 400 to 800, and in ultraviolet it is up to 400. Okay, up to 400 means it is 10 to 380 nanometers, or maybe 10 to 400 nanometer, and below 200 it is called the vacuum ultraviolet, because below 200 the air, since in your spectrograph or maybe spectrometer there is air, so therefore that air starts to absorb in the wavelength below 200 nanometer. Okay. So therefore that is called, that's why these instruments must be operated under vacuum if you want to study below 200 nanometer. So therefore your visible spectra is this, is the range, ultraviolet range is this, and we deal with this electronic excitation and de-excitation process. So, it is a typical overview of the frequencies that are used up. This is your, this region is your X-ray, that is where core electrons are excited. UV and of course visible, I mean UV of course visible, UV it should be UV visible. This valence electrons excited. Valence means loosely bound or like that, electrons are excited, not the core electrons. IR, here molecules vibrate, and radio waves, it is the NMR, for NMR, and microwave it is your, this is your rotation spectroscopy. Okay, that is molecules rotate in this region. I mean rotational energy falls in this region, and this is your visible part. 400 to almost 800 nanometer is the visible. This is your VIBGYOR, VIBGYOR. So this is the 7 colors. Okay, so this is a typical generalized representation of the different frequencies and the corresponding motions that are associated. Although I have not written over here this microwave, it is for your molecular rotational motion. Okay. Now, absorption of ultraviolet and visible light occurs in molecule have electrons with low excitation energy. It should be low, with excitation energy which is low. Okay. There is a typo, little typo, with low excitation energy. If the excitation energy is high, then it will be in the further higher energy level. So you see that if we think of the energy electrons in various levels, you see it is your bonding electrons, these are deep seated, okay, bonding sigma. Then bonding pi is little, it is little above this bonding sigma. Then it is non-bonding. Then these are all non-bonding. So this transition, that is bonding to anti-bonding, this is a huge gap. You see here, this is also widely separated. So this gap is very high, and basically it absorbs below 200 nanometer. Generally this is vacuum ultraviolet. Okay. Now for your bonding pi to anti-bonding pi, this has got high molar absorptivity, means it absorbs strongly. Okay. So this falls in ultraviolet, and in general it is ultraviolet and visible region. Ultraviolet visible region means the say maybe 200 to 800. In this region, these are most operative depending on the system of interest. Okay. Now next we have to, since we deal with spectroscopy, we should have some quantitative measure. Okay, we should have some quantitative measure. What is that quantitative measure? Now quantitative measure means, as I told you that when there is some specific frequencies available in the radiation, and that matches with the energy gap available within the molecule, then there is a possibility of absorption. There is a possibility of absorption then and only then. Okay. So how much it is absorbed? As I told you that those frequencies are either missing or missing to some extent, or it is diminished in intensity or diminished in amount. So how to quantify that? That we have to think about. Okay, so how to quantify that? Now that is why you use one law which is called the Beer's law. Beer's law means, Beer's law is basically, if you think of some light absorbing, system, then what happens? that say this is your incident intensity I0, this is your transmitted intensity I, then decrease in intensity is proportional to this thickness, this L, and also it is proportional to the concentration or the population of the molecules which are interacting with the radiation. Okay. So, this way if we formulate, I mean decrease is basically minus di divided by I is proportional to L and C, and then if we integrate it and put the appropriate things, appropriate numbers, then it will be log I0 by I is your some constant epsilon C into L. This is called your A, or called the absorbance. That is it is a measure of how much of light is absorbed or light is used up, or it is to what extent the light is diminished in its intensity. Okay. So, therefore, A is your epsilon CL. So, here this A is absorbance, it is called the absorbance, or sometime it is called the OD, optical density, and this is called the molar absorptivity or molar extinction coefficient, which is unique for a given compound, and it depends on the compound and also the wavelength. That is, it is very much wavelength specific. If you change the wavelength, then epsilon will also change. Okay. L is the path length, because if you have larger path, then the radiation will have chance to have more interaction, I mean interaction with more number of molecules. So, there will be more chance of diminution of its intensity. Okay. In the same way, if number of particles or interacting particles are increasing, okay, then what happens then is also, I mean that means the concentration, if concentration increases, then this absorptivity also changes. Therefore, this is a quantitative way to express, I mean how much of light is absorbed when something, I mean some light is passing through some radiation absorbing or radiation interacting system. Okay. So, this is called Beer's law. Okay. So, so this way we quantitatively can express the amount of light that is absorbed, and we this amount of absorption or the amount of reduction that we linked with this path length, the number density of the molecule, and also something which is very specific to the molecule, that is epsilon lambda, specific to the molecule and very specific to wavelengths. So, this way we quantitatively can express this I mean how much of light is used up or how much of light is not used up. Okay. So, what we have learned in this particular class. Okay, let us try to summarize. Okay. So, spectroscopy, what is that? If we say what is spectroscopy, it is a very important tool to look into various motions of the molecules. Okay. Various motions means maybe this quantized motion. Molecule means molecular systems are basically associated with quantum states, discrete energy levels. Okay. And these discrete levels are associated with various motions. That means maybe it is electronic motion, maybe it is rotational motion, maybe it is vibrational motions. So, these discrete energy levels we look at, and also in spectroscopy most importantly we try to find out the exact position. Position means we try to find out means exact energy of that particular level, and also during transition how much of energy is used up, and whether a particular frequency is used up or not. That is very important. When particular frequency is used up means that particular frequency or wavelength is very active, very characteristic for that molecule. That means the molecule must have that energy gap. Okay. So, it is an important tool, and it is I will come to the point that it is a very sensitive tool. I mean gradually we will come to know that it is a very sensitive tool, and it is used in many many places, like to know, I mean to identify certain molecules, I mean all molecules. You can in principle find out, or you can identify molecules. Also, if there is some specific interaction within the molecule, okay, if there is some specific interaction, that you can also find out. Okay. So, therefore, spectroscopy, although I have talked here about the absorption spectroscopy, so this spectroscopy is one of the important tools. I mean there are other like absorption, then emission, then resonance spectroscopy, maybe X-ray spectroscopy, but absorption spectroscopy is also a very important tool. Okay. It can be used to find out the population, because using this Lambert-Beer's law, using this Beer's law, we can find out means we can find out this population. If we know epsilon for a given molecule, if we know the path length, then we can find out C, okay, from a standard graph. So, these are very important. I mean this absorption spectroscopy is indeed important tool. Okay. So, in our next lecture, we will take up other forms of other spectroscopy which is relevant here, particularly with respect to this series of lectures, that is emission spectroscopy. We will take up in the next class. So, till then, have nice time. Thank you.